Let's do an example problem. In this case, we're going to subtract two vectors in 2 dimensions using components. So if you haven't seen how to do this graphically, I suggest you go back and watch that video. However, now we'll do one with numbers. Sometimes you have to look at each of them, go back and forth till you understand what's going on. And that's okay. Absolutely nothing wrong with that. Let's start by reading our problem. Isaac is walking with a velocity of 2.2 meters per second, 23 degrees south of east. So that's my initial velocity, or what I'll call v1. Why? Because it happens earlier in time. Later on, he is walking with a velocity of 2.2 meters per second, 41 degrees west of north. So that's my final velocity, or my second velocity. So I'll call that v2. What are they asking us? Determine the change in his velocity, or the difference in his velocity. So change, if I'm going to write this out, basically it's asking me to solve this, which is, what is the change in velocity? Well, delta v, by definition, is the final velocity minus the initial velocity. Anytime you see that delta, that means final minus initial. So the first thing I'm going to do is draw these two vectors and find their components. So let's look at the first one. First of all, let's define, oh, I did that the wrong way, but that's okay. Easy to fix on here. I'll just flip it around. I'll define which direction is north. So just out of habit, I always have north facing up. And in fact, instead of calling it north, I'm going to call it y. And that means that this way will be positive x. Do I have to call it that? Not necessarily, but let's use convention so we don't get confused. So maybe we want to tell ourselves a little something about that, put a little note. Y equals north, x equals east. Okay, so let's draw this vector and let's see what it looks like. 2.2 meters per second, 23 degrees south of east. So we'll say that's 2.2 meters per second, 23 degrees south of east. Would be roughly like that. How do I know that's south of east? Because east is this way, and I'm going south of east. Very important to get this drawing right. Now let's draw in the components for that. This is v1, by the way. So there we go. So let's indicate that this is v1. So that means this is v1x, this is v1y. And let's look at our second vector here, 2.2 meters per second, which means it's going to be the exact same length. So I'm just going to do a copy of this one, so we know it's the exact same length, but it's 41 degrees west of north. So that means we start with north and we go west. So, and we go west by 41 degrees. So that would be roughly there. Now we'll find the components of that one. So the components of that one are going to be roughly like this and like this. And let's write in the values here. This is v2. What's this one? v2x. This one will therefore be v2y. Now the thing we're going to need to remember is that we're going to be subtracting these, but we'll take care of that in a moment. Let's also figure out where our angle is here. So our angle here is 41 degrees west of north. And over here, our angle is 23 degrees. Okay, now let's figure out what all these pieces are. Now, what I'm going to do is I'm going to take all the y components and the x components. I'm going to add the x components together, or rather subtract the x component of v1 from the x component of v2, and subtract the x component of v1 from, the y component of v1 from the y component of v2. So I'm going to make myself a little table to help keep this organized. Nothing fancy. I just do it like this, and I go, okay, here's my, and actually I want a little more room just because I find it hard to write using this tool right now. I'm still not used to it. So remember, what we're doing here is going to be v2 minus v1. And I'm going to have my x component and my y component, like so. So let's think about v2. v2, we've got 41 degrees. If we look at the x component, it's opposite. So v2 sine 41 is going to be the value of v2x. So where I have v2x, it's v2, which is 2.2, and it's going to be sine. So this one's going to be 2.2 sine 41. Now let's look at the y component for v2. It's here, it's the adjacent, so it's the cosine. So it's 2.2 I'm going to erase that line just because I don't need it. Cos 41. Now let's look at v1. v1x is, well, once again, it's 2.2 is the velocity, and we look at v1x and it's adjacent, so it's cos. What's my angle? 23. And here I've got 2.2 sine of 23. Now I'm going to stop and think for a moment in all of these cases in terms of what's positive and what's negative. For the y component of v2, it's pointing up, so that's positive. But v2x, which direction is that pointing? It's pointing to the left, so that means it's negative. So that means in front of this, I'm going to put a negative sign in front of v2x. And then in terms of v1x, it's in the positive direction. But look at v1y, it's in the negative direction. So that means for v1y, I need a negative sign as well. So now I carry out the operations, not forgetting that I am subtracting. So I like to do this on the calculator all in one go. So let's pull up a calculator, and we'll get the value here. What do we have? Minus 2.2 sine 41. So minus 2.2, and this is an unfamiliar calculator for me, so minus 2.2 times sine of, oh, you know what, I'm using this calculator wrong. Let me start that over. Minus 2.2 times 41 sine of 41 minus 2.2 times, this one's the cos of 23. So what I've done is I've entered all this in one go. Remember, I have to take into account this negative sign. So I get minus 3.4 So keeping the right number, I'm going to keep a couple of extra digits, minus 3.46. So the resultant, so for delta V, the resultant here is minus 3.46. Let me just double check that I wrote it properly. Oh, it's 4, look, it's 468. So really I should round that to 47. So in terms of my resultant, the x component is minus 3.47, which means it's pointing to the west. Okay, now let's look at the y, and let's enter that into the calculator. So we'll clear this. So we have 2.2 cos 41, 2.2 times 41 cosine equals 1.6 whatever. Now we're subtracting, watch yourself, this is negative, negative, which means we're going to add those two together. 2.2 times the sine of 23. And what do we get? 2.519. So 2.52. So those, remember, are the components of the change in velocity. So if I write them down, first of all, negative x means this direction, and it's 3.47. It's a pretty big one. And 2.52 is in the positive direction for the y. What that means is my resultant looks like this. And I actually can find a value for that if I use the Pythagorean theorem, because there's an angle. Remember, this one here is minus 3.47. So because it's pointing in the right direction, I'll just put 3.47. This one's pointing in the right direction, 2.52. So using the Pythagorean theorem, I just square and add those. So 2.52 squared plus 3.47 squared equals, and then I want to take the square root of that, so I just hit square root, equals 4.2. 4.288, so 4.29. 4.29 meters per second. So the change in velocity so we're almost done because we have the magnitude, but we need to find this angle. And that angle is, so let's think about it, the tangent of that angle is 2.52 over 3.47, so the angle itself is the inverse tan of 2.52 over 3.47. So if I punch that in my calculator, once again, 2.52, no, that's not right. 2.52 divided by 3.47. I'm going to get this value, and then I take the inverse tan of that, and I get 35.98 degrees, so it's really 36.0 degrees. So now I'm ready to write my final answer. Now I'm going to go back and look at what I was initially given. Two significant figures, so my final answer should have two significant figures. I kept three through, more than two throughout. In fact, I've got three here, which is good practice. That way I don't end up with a creeping rounding error. So let's have a look. My final answer should be 4.3 meters per second. So change in velocity and it's a vector, so let's give it the physics party hat. is, what's my value? 4.3 meters per second. And my direction is 36 degrees. Now let's look at this. I started west and I went north. So it's north of west. So let's just consider why that might make some sense. If we go back to my initial vectors, and I have v2 minus v1, and I try to add those together sort of the way we used to, just graphically. Let's have a look at that. I take this one, and I just want to graphically put them together, and I take this one. Now remember, when you're subtracting, so here's v2, and here's v1, what do? We oh, come on, give me the whole thing. So I want to rotate it. It won't let me do it nicely. Okay, let's see if I can do it this way. Rotate. We can flip left to right. Flip. Up, down. So basically I've changed its direction. It was pointing this way, and I've changed it so it points the other direction. And so my resultant, when I put them toe to tail, is this big long vector that looks like that, which is kind of what I ended up here. Of course, the scale is different, but that's certainly makes sense and is pointing in the same direction. So rather lengthy procedure, but you need to learn it.